We are alive.
Okay, shall we continue then? Okay, I think she's not. She's having a little bit of trouble, but anyway.
Yes, please.
Okay. So, yeah. So again, continuing with the honor of introducing part of the most remarkable theoretical physicist from Germany, it's now my pleasure to introduce in the spirit of the previous talk, one of my mentors and one of my best friends to whom I personally own a lot. It is my pleasure to introduce now to her Professor Dr. Thomas Voigtmann, one of the most notable physicists, theoretical physicists working among many topics in the fundamental description of the glass transition. Thomas got his PhD in München, working with Wolfgang Goetze, and continued with postdoctoral positions in Edinburgh and Rome. He's currently an editor of Physical Review E, and is also head of the Theory and Simulation Group of the Institute of Materialphysik im Weltraum from the Deutsche Zentrum für Luft- und Raumfahrt. And he's also a professor at Heinrich-Heine University. And Thomas, I want to thank you personally to accept this contribution. And even though I told you and asked you so late, and it is as always a pleasure to see you. Thank you very much.
Thank you, Luis, for this slightly overwhelming introduction. It's now difficult for me. I mean, I should say, okay, I'm not an editor of IFUASLP, that just to correct that, I'm on the editorial advisory board, but and I don't have all those stories to share since I don't don't know him for long enough. But I remember a particular meeting in 2018 where I also got to know Luis, that Magdaleno organized in San Luis Potosí. And as it so happens, I am now in Copenhagen, and I'm actually working at Roskilde University, and I spoke to Jeppe Dure this morning. And Magdaleno, he sends his warmest greetings, and pointing out to me that you have, that he considers you a close friend, and that you also have a lot of stories to share.
Yeah.
Thank you. Okay, so let me jump into my presentation. And I thought, so we heard Stefan and Marco talk, and there has been a work with many contributors, many of whom are in this meeting, on binary mixtures that actually Luis was heading in terms of leading this collaboration and things. So I guess I could have also wondered whether I should talk about that, and then I decided maybe not. I'd rather present some ideas that I had recently on aging that are pretty much inspired by Magdalena's work, I should say. And this is actually work done with Luis Fernando. And in the time where he was at the DLR in Cologne, and where we established what you can call the Mexican mode coupling connection. And I say why I call it like that. And of course, besides the head of the institute in Cologne, Andreas Meyer, I should really thank Magdaleno for his hospitality and laying the foundations of what is to come. So the topic is going to be aging dynamics in hard spheres, and I'm going to consider the simplest aging experiment that you can do, arguably, in hard spheres. So we start with a system on the left. I'm sorry, I need to close the window. We start with a system on the left, which I imagine as a hard sphere system that is moderately dense. And then we make a sudden quench from some initial packing fraction to a final packing fraction, which is higher. So we end up in a situation depicted on the right. And then, of course, even if we started in equilibrium, now we're not. And the question is, what is the dynamics of the system as it evolves slowly? And of course, as we all know, this will become particularly interesting if the final packing fraction is in the vicinity or even beyond the glass transition of these hard spheres. And I'm really carrying coals to Newcastle here, or Eulen nach Athen, as we say in German, because the experiments I'm going to refer to, the computer experiments, are all performed by some of you, all of you, I don't know, I mean, like many of you in the audience. So let me just bring everyone on the same page what I want to talk about. If we look at simulations for hard sphere-like systems after such a quench, you can start by looking at the structure factor. So here's the static structure factor as a function of waiting time after the quench. And I just want you to look at the symbols. And what you observe is that in particular near the main peak of the static structure factor, the structure gets more pronounced after aging. And if you perform a quench to a point that is not yet dynamically arrested, after some waiting time, the evolution saturates and so the structure evolves from its initial state to its final state. And it gets more interesting if you look at the dynamics. So exemplary case here is the self-intermediate scattering function. You see this recorded after various waiting times after the quench. So you start measuring at waiting time TW, and then you perform correlations to TW plus a time that is called tau here. And you see as the waiting time increases, the signature of slow dynamics more and more evolves and becomes more pronounced. So what you can do to characterize this a bit is to look at the structural relaxation time, and make a plot of how this relaxation time evolves with the waiting time. And again, these are figures that I took from an influential paper, at least for me, from you guys, I should say, and coming out of Magdalena's efforts. And so just to reiterate, the structural relaxation time tau alpha evolves as a function of waiting time after the quench in two characteristic ways, depending on where you quench to. So if you perform a quench from some moderate packing fraction to, let's say, a packing fraction of 56% in this hard sphere-like system, you will see that the alpha relaxation time eventually saturates to this new equilibrium value. And equilibration takes longer and longer the slower the system is, the closer we quench to the glass transition. And there seem to be state points where it's compatible with having a glass transition around 58% of packing fraction, where this aging evolution continues as long as you can simulate. You can also look at this same plot in different cuts. You can make cuts at constant waiting time that kind of mimic what you might do in experiment. If you have a specific time scale connected to your experiment, then you would measure relaxation times that are not necessarily equilibrated, but recorded after a finite waiting time after preparing the sample. And the message then is, as actually we all know here in this audience, that while the relaxation time is predicted to diverge or grow very strongly as we approach the glass transition in equilibrium, if you're not patient enough, you will at some point see deviations in your measurement from this curve that are a signal of finite waiting time dynamics and the system not yet being in its equilibrated or at least stationary state. Now, so this is just summarizing what I want to focus on from these simulations. The static structure evolves from some initial to some final state. Maybe it doesn't ever get to the final state if the system becomes dynamically arrested in between. And there's a structural relaxation time that should be tau alpha probably, or could be a k-dependent quantity that also increases with age of the system. And what Magdalena would now do is to present a theory that is the non-equilibrium self-consistent Langevin equation theory, or self-consistent generalized Langevin equation theory, which, as I realized after a while, really consists of two parts. One is the generalized Langevin equation theory, and the other one is the non-equilibrium part of it that, as Magdalena points out, is derived starting from Onsager principles. And it looks very generic and so. I recently thought maybe I can translate this into a language that I'm used to, that I grew up with. As Luis was mentioning, I grew up in Goetz's group, and there we really do stuff with projection operators and similar things. So let's have a look. If we want to describe the time-dependent dynamics of the system, we should look at the time-dependent probability distribution function of finding certain configurations. And I'm going to write this very generally. This is usually a partial differential equation. So omega usually is a differential operator. It might depend on time if we drive the system in a time-dependent fashion with some time-dependent external force. So what we have here is really my shorthand way of writing a Fokker-Planck, Smoluchowski, or Liouville equation. And if you write it as compactly, you can write down the formal solution also rather easily. So this is going to be an exponential function. And since we're dealing with operators here that might not necessarily commute with themselves, at unequal times, we have to do path ordering, and the formal solution is given by the forward path ordered exponential of applied to some initial state. And then there's a little trick in rewriting this. So I basically can express the current probability distribution function at the time t I'm interested in, compared to some reference state I might know, as a history integral over complicated stuff applied to whatever reference state I might know. And we don't worry about the second part of the slide. This is just to clear some names, but I don't think I need to go into that now. And so far it's just a formal manipulation. And it's a formal manipulation that really became popular following the work of Mike Cates and Matthias Fuchs in colloid science, where they applied it to describe colloidal systems under shear and other things meanwhile. And there the idea is you do a nonlinear response theory, if you like. So you basically say, I assume I have a time evolution that I call omega 0. So this would be the unperturbed Smoluchowski operator in Brownian dynamics. And then I have a time-dependent perturbation that I switch on at some time. And I don't assume this perturbation to be small at all. Just making use of the fact that my initial state, so that the initial probability distribution function, I can choose to be at least the stationary state of whatever dynamics I had before the perturbation. I can just go back to the previous slide and rearrange terms and write the probability distribution function at time t, which is in non-equilibrium, as a history of integral of some differential operators applied to the stationary one. And if this is actually an equilibrium one, I'm lucky enough that this can often be calculated precisely. And so this is where this usually comes from. And then you say, okay, if I'm interested in some observable f that is a phase space or configuration space variable, its time-dependent average is the observable integrated with the time-dependent probability distribution function. And then I can express this in terms of a stationary average and a history integral over a correlation function. And if I would now do linear response, I would replace the time evolution in this object by the equilibrium one, and I would have a Green-Kubo relation or so on. Some people even call this the fluctuation dissipation theorem already. But I don't want to go into that now. I want to come back to the idea of a quench. So naively, what we're doing, let's say we quench the system at time equals 0. So that means I have some initial state with its presumably equilibrium time evolution omega I. And then I imagine doing something like changing the confining potential to mimic a compression that I perform suddenly or something. And then I end up in a final state with its time evolution. So I just apply this step function to my formulas. And then, as it turns out, it makes sense to describe the probability distribution function that characterizes the system awaiting time tw after I perform the quench, with reference to whatever it might want to be a long time after that quench, so the final state. And again, just plugging into the previous equations, you get a history integral over some propagators applied to something that I can write as the time derivative of the probability function at time tw. And again, now I could be interested in averages of observables to calculate, for example, the waiting time dependent structure factor and so on. And however, this is too complicated for me. So let me do something that is actually in the spirit of mode coupling theory. Let's just be true to this integral and split it by inserting a projected dynamics here by saying I only care about the evolution of density pair fluctuations here. So I project onto density pair fluctuations. And well, then if you do that and you use this to calculate the static structure factor, which, as we all know, is just the waiting time dependent average of squared density fluctuations, I get an equation that starts looking like this, and then after rearranging term, it looks like this. So what I get is that in this very crude approximation, the way I present it, the waiting time derivative of the evolving static structure factor is something that looks like exponentially relaxing towards its final state with a mobility or inverse relaxation time that we can, in fact, approximately relate to the integral over the density correlation functions. So this starts really looking like mode coupling theory, the integral of the square of the density correlation functions. And this equation, it turns out, is actually well known. And well, by whom is it well known? And this is why I wanted to talk about this here. And this is, of course, one of the equations that are at the foundation of the non-equilibrium self-consistent generalized Langevin equation theory. And you find it everywhere, even on Instagram these days. So in a somewhat more obscure form, I should say. But anyway, so there are many things you can do now about this. And just to mention one mathematical way of solving this is to say, well, if I have a function that's a function of tw here, but the relaxation time is a function of tw, it makes sense to transform the time so that I can write the structure factor in terms of a so-called material time as a simple exponential relaxation. And this is really something that I found very inspiring to read about in recent work that came out of not only Magdalena's group, but out of a whole of different groups in Mexico doing all similar developments there, I should say. And let's, what I can do now further on is I can steal a slide from Magdalena, finally. So this slide is deeply inspired by what I heard Magdalena talk about for many times. Because you can say this equation is interesting because it predicts that the evolution of the structure with waiting time might get stuck for two reasons, because I have two factors here that can be zero, either one or the other. And to go back, so if the relaxation time always remains finite, then of course a stationary solution is if the structure factor attains its final value. And I should remark here that Magdalena is even more careful in writing stuff here. He is also worried about quenching into states where the static structure factor as such doesn't even exist. So you could generalize this object a bit, but just to get the idea. So if the relaxation time is finite, which typically will be if we quench to a state that is below some critical density, then the long time limit of the structure factor will be the equilibrated static structure factor. However, if the relaxation time happens to diverge, then this prefactor here becomes zero, and that's also a stationary solution of the equation above, which we will typically encounter if we quench to a point that is larger than the glass transition. And then even if we wait indefinitely, we might not ever get to a stationary solution of the structure factor that we quench to. So there is the possibility of possibly indefinite aging. So you see, now I'm back to repeating what Magdalena already knew. But together with Luis, we sat down and said, well, it should be possible to say something about how the relaxation time, the waiting time dependent relaxation time, will either equilibrate or continue to grow as a function of the waiting time. And to see what we can do there, I need to jump back to a dreaded slide with formulas about mode coupling theory, but I guess in this audience here, I can actually do that. The point here is that it's something that in a paper that you can read about here in Physical Review E, and we managed to get it in volume 100, which is always nice to remember. So Luis and I, we looked at the mode coupling equations I was familiar with and the self-consistent generalized Langevin equations Luis was familiar with. And well, if you look long enough, you say, well, they have the same structure. They are integral differential equations with a memory kernel, and the memory kernel is provided by a self-consistent closure. So that becomes clear, and then you think about the differences between the theory, possibly. And the differences are there, but they are quite interesting and subtle. So the differences come from the fact that mode coupling theory basically starts from thinking about the collective dynamics, and then says, if I want to understand the glass transition, I have to understand how everyone collectively becomes slower. And then if I'm interested in something that we can more easily measure, let's say the mean square displacement or the tracer density fluctuations, I write down equations for the tracer that are enslaved to the collective dynamics. So in terms of MCT, what you would say, there's a memory kernel governing the collective dynamics. And the mode coupling theory says this, I write as a quadratic functional of the collective density correlation function. And this will depend on wave vector, and it will also, the vertices will also depend on the static structure factor. And actually there is a way of deriving these equations for the aging setup I discussed, where it will actually be the waiting time dependent evolving static structure factor here. And then if you're interested in the self-dynamics, well, you write a separate equation with a memory kernel for the self-dynamics. That is a very similar looking functional, which is now bilinear in the collective and the self-dynamics. Magdalena's theory comes from the other end, if you like. So he would say, well, I can look at one particle and I see that if the particle is embedded in a glass forming liquid, it will experience friction that becomes extremely slow. So I can start right away by writing down equations for that tagged particle, and they will have a friction memory kernel that is, again, a bilinear function of the collective dynamics provided by the bath particles and itself, the self part. But what you then do is you need an expression for the collective dynamics. And here the self-consistent generalized Langevin equation theory says we can make a slightly different functional, but it should have the same form as the one that we employ for the self-dynamics. So here also the self-dynamics enters. And that turns out to be the main difference between the two theories. Otherwise, they are mathematically really almost identical, I should say. And as I said, I won't go into details here. You can check the paper. We managed to find some cases where they provide very different predictions. And there are some very interesting things to be said about mixtures and partially arrested glasses. But for the hard sphere system I'm talking about here, both theories are mathematically identical in a sense that we can even formulate. And if you remember, what Goetze was very proud of with his theory is the so-called beta scaling laws. So there are very clear predictions of how the correlation functions decay towards their plateau value and from their plateau value. There are power laws hidden in how the timescales diverge as you approach the idealized glass transition. And it turns out exactly the same scaling equations hold for the self-consistent generalized Langevin equation theory. So the only thing that changes are the numerical prefactors. So if you recall, mode coupling theory predicts power law divergence of relaxation times with exponents that are not universal because they are given by the static structure factor of the system. And in principle, the self-consistent generalized Langevin equation theory predicts exactly the same, but the way you calculate the exponents from the structure factor is slightly different. So you get different numbers, but that's pretty much it. And then when I saw this, I said, yeah, well, this I can use now, because now we have scaling laws for aging. And to see what happens, let's recall that we imagine placing ourselves close to the glass transition. We quench close to the glass transition. We look at the dynamics in a window where the system is close to its glass transition. So there's a distance parameter that variable is called either sigma or epsilon. There's a subtle distinction between the two. So basically the control parameter difference to the critical temperature, or in our case, the critical packing fraction. So that's a small distance parameter. And we know that at the glass transition, the static structure doesn't change dramatically. So I can Taylor expand. I can Taylor expand the structure factor, whatever it may be, in terms of the distance to the glass transition. But then Magdalena's equation for the evolution of the structure factor becomes an equation for the evolution of the distance parameter. And it reads like this. So we change our distance to the glass transition in this exponential fashion. We try to approach the distance that corresponds to the state we quench to. But the relaxation is governed by a mobility that is also a function of how far we are currently away from the glass transition. And now comes the trick. Now here we can insert the scaling laws. And here on this level, it doesn't matter whether we're talking about mode coupling theory or the Langevin equation theory. It's going to be the same power law. Gamma is going to be some exponent that we can calculate. It's going to be 2 point something for a hard sphere system. But that's it. So both theories predict that the mobility goes to 0 if the distance parameter is less than 0, which is chosen to be the liquid state. And so I'm sorry, I just realized that these absolute values here should not be there. And distance parameters greater than 0 correspond to glassy states, and there is no mobility left. And now things become easy because you just insert this power law here, and you can analyze this equation by hand. And it turns out there are basically 3 regimes that you could be interested in, and they are basically distinguished by whether we quench to a value that is very close to the glass transition, so where this sigma final is very small, or whether we quench to a state that is deep in the glass, where this is big and eventually dominates the other terms. And it turns out if we quench to a state that is very close to the glass transition, and we neglect this term, you balance the powers and so on, you find that the relaxation time is predicted to grow linearly with the system age. So that is what people have called normal aging, and it's recovered here as one scaling law in an asymptotic sense. You can also quench to a state that is deep in the glass, and then this number will be big, and it will eventually dominate the others. Then balancing different powers, you get finally that the relaxation time is predicted to grow like a specific power of the waiting time, gamma divided by gamma minus 1. Now, as I said, the exponent gamma, as predicted by both theories, is actually bigger than 1 and bigger than 2. And that is actually a limit that you can prove. So we know that this exponent here is bigger than 1. The relaxation time of the system grows faster than the waiting time after its preparation. This has been occasionally discussed in the literature. I come back to that in a few minutes. You can call it hyperaging, and we find it here as an asymptotic law for a deep quench into the glass. You can also, of course, quench into the liquid. Then it's a bit more boring because the relaxation time is almost always finite, and then you obviously find that the relaxation time approaches that constant after a while, so you have equilibration. As we shall see, this gives rise to something that looks like what people have called sub-aging, that looks like a regime where the waiting time grows sublinearly, where the relaxation time, sorry, grows sublinearly with the waiting time. So let's see what we get. What I have here are as symbols, again, shall I say, your simulation data. And it's the same plot that I showed before. I've just inserted my own fits using a theory. I'll say a word about that. Those are the lines, the colored lines. But let's start with the asymptotes. So I've drawn the asymptotes for a quench exactly to the glass transition, where asymptotically the waiting time should grow, the relaxation time should grow like the waiting time. And here's the prediction for a quench deep into the glassy state, inserting the numerical values for the exponents that one expects for Hart spheres. And well, you can see the colored lines, which are the solution of the theory. So the theory here agrees with the theory, that's fine. And we shall come to discussion of whether they also agree with the data in a minute. Just as a remark, if you plot the relaxation time as a function of the waiting time in a double logarithmic fashion, and you have something that starts out being in a stationary state and ends up being in a stationary state, whatever happens in between, if it's monotonic, is always going to look like a power law. So of course you can always try to fit a power law with an exponent that is slightly less than 1 here, and it seems to work. And that actually matches what I found in the literature on various claims of sub-aging. So I would argue that this is a crossover, and that the true asymptote is for the quench to the glass transition where it's normal aging, and potentially hyper-aging if you quench into the glass. So the colored lines are actually a hybrid sketch theory that takes Magdalenos evolution equation for the static structure factor and combines it with the schematic model of mode coupling theory, because that's something that the mode coupling community has always been strong in saying, oh, we are too lazy to solve the full equations, so we make schematic models of which we make sure that they recover the same asymptotic laws, and we can even use them to fit data because we have some free parameters that we can tune. And this is exactly what I did here. So you see, you get a rather nice fit of the simulation data up to a certain point. And then for the two deepest quenches, for the two quenches to the highest state points that you had in the simulations, yeah, there are 4 points that are really falling off this predicted asymptote. And that's, of course, that's a pity. Because in principle, you could argue that this regime of hyperaging, which might be an interesting prediction, is maybe not entirely convincingly seen in the simulation. But we come back to that. Just briefly, here's the different representation, the one that I also stole from your papers, which is the relaxation time drawn for fixed waiting times for quenches to specific points. So this is not, it's basically a packing fraction here in terms of a distance parameter. So if we look here, this would be 4 quenches to exactly the equilibrium glass transition point. And you see there's a black dotted line here that diverges. This is the equilibrium prediction. And again, it's either of mode coupling theory or of the self-consistent generalized Langevin equation theory. And the colored lines are my hybrids using a schematic mode coupling theory together with Magdalenos non-equilibrium aging results. And it's the same fit that I was using here. So it's just that in a different representation, you see deviations differently. So I'd say this looks very convincingly. I can even calculate asymptotic behavior for the shape of the curve here. And the only problem is that if you look closely enough and you're not colorblind, you realize that the dark red here should actually be up there. And these pinkish reds belong together. And it's the same problem that we encountered here, that at some point the prediction of the theory is far larger than what is actually measured. So we need to come back to this. And this is what I want to indicate rather briefly, because it covers an interesting point that I discussed, or I remember a fierce discussion that Magdaleno and I had, I think 3 years ago, when we had a small meeting also with Luis and Andreas Meyer. And it concerns the question of whether the critical point of the non-equilibrium self-consistent generalized Langevin equation theory, is actually corresponding to the glass transition as measured by experimentalists, or whether it's still, as we know from mode coupling theory, a critical temperature or critical packing fraction that is unfortunately not the calorimetric glass transition. And of course, qualitatively, it's very tempting to say that we have a better theory now, because we have a point where the relaxation time would diverge if we waited infinitely longly. And you would argue that this is a packing fraction just above phi g and not phi c. So, however, I would argue that these 4 points that I was mentioning here before tell us a more interesting story. And this is where I'm now building our hybrid theory even further. And I want to include an idea that Tommaso Rizzo and I recently developed. It was really something that he came up with, and then we sat down together to implement it, which is the attempt to include fluctuations beyond mean field in mode coupling theory, actually on the level of the scaling equation. So it would actually conceivably also work for the generalized Langevin equation theory. And the idea there is as follows. So again, we have here an audience to whom I can show this, I guess. So what we have in the center of the slide here is a version of the beta scaling equation as originally derived in the context of mode coupling theory by Goetze, with a few added terms. So let's walk through them. In the original theory, you had a distance parameter sigma to the glass transition. And there was a scaling function called g of t, the beta scaling function, that obeyed the following equation. It had a parameter lambda, which is called the exponent parameter, times the square of the function is balanced by the convolution of the function with itself. And on the other hand, we just have the distance to the glass transition. And if you set the distance to the glass transition to 0, and this term was also not there, then you have a g squared equals the convolution of g with g. And it's easy to convince yourself that power laws are the solution of this equation, and hence the famous power laws of mode coupling theory. And now the idea that Tommaso came up with, and you can read about in his papers, is to say that actually there is a rigorous argument that you can use borrowing ideas from replica theory, that what should happen in beyond a mean field level in a certain sense is that there need to be fluctuations of this, if you like, dynamical order parameter. So whatever was a constant sigma needs to be a spatially dependent fluctuating quantity. So it has a mean sigma, and there should be zero-centered Gaussian fluctuations around it. So the picture is a little bit like I tried to sketch here. Never mind the axis, but if you imagine, for example, the density in the system to have spatial fluctuations on long wavelengths, and there will be some regions that happen to be dense enough to be glassy, and some regions happen to be not dense enough to be still liquid-like. And you can express this in terms of a fluctuating distance to the glass transition point. And then arguments from replica theory suggest that what you need to do is you need to extend Goetze's beta scaling equation by a spatially fluctuating component. So then everything becomes a function of x, which is just real space. And here as well. And if everything becomes a function of x, then in terms of this perturbation, you would also expect a gradient, or actually gradient squared for symmetry reasons. So there might also be this term. We figured out it's not very important in understanding what's going on. But the important thing is that you have a collection of, so to speak, patches in your system. Some of them relax slowly, some of them might not relax at all. And this is then the equation you should analyze. And then something interesting happens. Actually, intuitively, it's clear if I quench the system into the glass, so on average, the distance parameter will be glassy. I will always find however rare fluctuations that locally mean that the system has a local liquid-like patch. And according to the theory that we developed, the prediction is that these liquid-like regions trigger relaxation and therefore prevent complete dynamical arrest. So the relaxation time diverges in the ideal glass, but if you include fluctuations in this way that Tommaso suggested here, the relaxation time will never truly diverge. It will change nature across the mode coupling transition because it will change from something that's governed by the mean distance parameter sigma to something that lives in the Gaussian tails of the distance parameter, from something that is glassy, on the liquid-like tail. And you can then derive scaling laws how the relaxation time and the mobility or diffusivity should behave as a function of the distance parameter sigma here. And it's a bit more complicated than the usual power laws, but it's nothing that cannot be calculated. And there's an interesting fact that I want to sneak into this talk, that superficially what you get here is something to the power of b times gamma. Those are both exponents that we know how to calculate from the beta scaling equation, to the power of -1/b. So if I could just multiply them together, I would have something to the power of minus gamma. And the mobility would be something to the power of plus gamma. And if I form the product, it would be approximately constant. And this is exactly what happens on the liquid side of the mode coupling transition. But if you have these integrals over Gaussian fluctuations, this argument is actually no longer valid. And it predicts something that when I first saw it, I thought was utter bullshit, to be honest. It predicts what has been called a fractional Stokes-Einstein relation. So there you go. Just as a reminder, so we are used to the fact that in systems close to the glass transition, all the relaxation modes are really strongly coupled to each other. So basically that means that if I look at the diffusivity or at the inverse relaxation time, it's not a big difference. It's not a qualitative difference. So the way this is usually expressed is by saying that d times eta, or d times the structural relaxation time, is asymptotically constant. And a nice way of checking this is to just make a double log plot of the diffusivity versus the viscosity in proper dimensionless units. So you have to be careful to also take out the factor of kBt. And then if Stokes-Einstein holds, this should be a line with slope -1 here. And what I'm showing here are computer simulation data by Hailong Peng for the famous Kobe-Anderson mixture, and also a model of copper zirconium. I mean, I work at the German Aerospace Center, and there are a lot of people interested in metals, and so we occasionally have to do something where the atoms have names. And so you see that for high temperature, high diffusivity, low viscosity, Stokes-Einstein holds, and then it crosses over to something that you can fit with a power law with an exponent that is not 1, not -1. And it is very well predicted by Tommaso's extension to mode coupling theory, the so-called stochastic beta relaxation theory, which is the solid line here. And so that as an aside, and that I found motivating to investigate this theory further and to come back to our aging problem. So here's the plot again. I took data from simulations of you guys. We had the fit with schematic mode coupling theory, which of course predicts an ideal glass transition. It predicts this hyper-aging regime. And now I'm saying, yeah, but here with these 2 points here, I should really acknowledge that if I quench into the glass, there might not be an ideal glass. So I need to include not only mode coupling theory, but the stochastic version of it. And if we do that, the fit looks like this. It doesn't really match here. If you see that, this is because the thick two lines are only the asymptotic expansion and not the full schematic model. But you see, this is what would happen. And then I think we have a rather nice description of the data. I expect there to be some error bars also in this point here. So at least I'm happy with that. And it's nice because it starts looking like a complete description of the data. Mathematically, I was a bit disappointed because I was rather excited about predicting from a theory aging that is superlinear. And it looks like this is completely cut off as soon as you acknowledge the fact that there's not an ideal class. But actually not. And the way to see this is to divide the structural relaxation time by the waiting time. Now, if the structural relaxation time should actually grow faster than the waiting time, this function here should increase as a function of waiting time at some point. So this is linear log now. And I did that with all the simulation data I could extract from the papers that you guys have written. And so these are two different simulation data sets that we're seeing here, but for comparable systems. And well, I would argue that there is an indication of an upturn here. And it would really be fascinating to have more data points there. And for comparison, as solid lines, I plot the predictions of the non-equilibrium version, Magdalena's theory combined with Tommaso's and mine theory. So we're really putting everything together here. And you see this matches quite well. So I would say this is something that needs to be explored more. There might be arguments against hyperaging. You might find it strange that the system has a relaxation time that grows faster than you can actually ever wait. Interestingly enough, and Stefan might be the better expert on this, people have seen this or claimed to have seen this in physical gels. You have to look very closely. So check the papers, but this is a figure from the paper already blown up 5 times. And then you have to look into the inside and you have to see that this line here is not a linear relation between tau and TW, but superlinear. So at this point, I think you just have to believe the authors or me at this point. Same here, but there are some indications of hyperaging. So this grows faster than the waiting time, and then it levels off again. So this is not unlike what we're seeing in our theory. So let me conclude. I really wanted to share this with you because I think it's a fascinating combination of how we go round in circles. Like I started with mode capping theory, and then I encountered Magdaleno and learned about something that Luis has repeatedly called the Mexican mode capping theory. And then when Luis joined my group, we started looking into the connections between the two theories in earnest. And I spoke to you about the scaling laws that we find. And now we can try to go back and do something that with mode capping theory, we haven't been able to do so far. We can discuss why. And look at the aging problem and use all the knowledge that we have from both theories combined to derive some scaling laws for how the structural relaxation time evolves with age. There are many more things one can look at now. As I said, partial glasses and the partial equilibration, if you quench into a state that is partially arrested, might be extremely interesting. And Luis is currently looking into that. And I've also seen work where you start looking at cycling of quenches. There are some rather established in the literature signatures of glassy aging that one can probably start looking at now with a more theoretical background. So that's it from my side. I want to really thank you again. And I thought, I mean, the picture of Magdaleno that Stefan showed, we have seen quite often. So I found a picture that is really closely connected to this work. And this is from 3 years ago, where we met with this charming lady in San Luis Potosí. Yep, I leave that on. And thank you all for listening. Thank you for having me here. And thanks, Magdaleno, for always being full of hospitality and encouragement. And yep, I'm happy to take questions.
Okay, thank you, Thomas. It was a very, very exciting talk. And before taking questions from the participants here in Zoom, I will read just one question that came up in our YouTube transmission. So this question is from Jorge from Puebla. And he says, I find very interesting the formulation in this talk. I'm more of a condensed matter researcher. I would like to know if the speaker relates his formulations to strong correlations in superconductivity, for instance. There is a good debate of glass states in liquidity in the quasi-particles of condensed matter. Sorry for the back point. Now that I see the formulation of the talk, I perhaps like to know if the relation of the formulation of the talk with the Landau copper pairs in superconductivity.
Oof, that's a very good question. I cannot say I feel confident answering it. Maybe Magdaleno would actually, because the way of deriving the aging equation for the static structure factor, he has a way of deriving it that is more in line with what you were asking about, I would say. And so actually, if Magdaleno wants to answer, I'm happy to relegate the question.
I mean, this is my explanation. Thomas, don't put me to work. No, the point is, that's a good question. Because
it's YouTube. I don't have it.
Oh. I think that one of the things that we would like to try is in our approach using Sager's formulation.
Just a second, Thomas. Can you please put perhaps your microphone? I think there is a feedback. Exactly. Now you can.
Okay. Yeah. Okay. What I was going to say. One of the differences between mode coupling theory and the self-consistent theory is that the fundamentals, the very basic fundamentals that are taken from Moritz-Zwanzig projection operator. In the case of mode coupling theory, we take it from Onsager's. The main difference is that Onsager theory is a more phenomenological theory. It is a phenomenological theory. It doesn't claim to be rooted in the mechanistic, let's say in the microscopic description, and to do a projection. And instead, it profits from symmetry conditions, very much like in Noether's theorem, that you say there is this symmetry, there is an invariance, and hence there is a conserved quantity. Now, when you go from one very specific approach like Moritz-Zwanzig that uses the Hamiltonian and Liouville's equations and so on, then you have to remain faithful to that origin, so to say. Whereas in Onsager's theory, you say very general statements. Now, I say this because when you say very general statements like stationarity instead of equilibrium, then those many of the things that you say may be applicable to systems which are not in equilibrium, and that's the way we went to do this non-equilibrium theory. Now, but for the same reason, it may be that we haven't done that. That if instead of a classical system you say now I have a system of electrons, there is no in principle impediment to use the same approach and to write the general equations that symmetries allow you to write. Okay, this is something that I would love to do sometime, that I'm sure that I will not. And then good candidates would be precisely quantum systems and so on. But that's nothing that we have done. But it would be nice to put that in the agenda, but I know that the agenda is overwhelming. So anyway, that's all I have as an answer.
Okay. Maybe I can also say a couple of words to this. I try to share my slides again. So the thing is, I mean, the evolution that we describe for the structure after the quench is really this equation here. And when I saw this first, I said, this can't be right. This looks too much like just exponential relaxation. And there are memory effects in highly correlated systems. And the way we formulate them, and also in Magdalene's theory, they only enter here. And I thought, well, maybe that's not sufficient. Maybe there should also be a memory term in this equation. And this is something I have to admit I will just, I just need to look at more, and hence my different way of deriving this equation. And when you see how I derived it, it is exactly making a projection in a more complicated object here. So I actually start out with something that has a memory integral, and we split it. And in the context of glasses, we might be lucky because we know that this kind of projection onto density pairs is a really nice, it works really well. And then you end up at an equation like this, where you keep the memory effects only in the relaxation time, so to speak. But it's something that should be explored better, I guess. Other than that, also the formalism I'm using here, of course, can be written down in nice analogy also in quantum systems. Right? It's you basically can work through the whole stuff that is the formal manipulation of an equation of motion, and there are quantum versions of that, but I haven't looked into that myself yet.
Okay, thank you very much, Thomas. Questions from the audience here in Zoom? I think if anyone wants to contribute with a question, commentary. I think Gerhard was mentioning yesterday about the connection between the Langevin approach and the MCT approach. I don't know if you want to contribute a little bit, Gerhard. Well,
yes. Actually, maybe I can repeat my question. I mean, this is actually just a comparison between. So you answered the question already partially, but if you would do, say, for a certain type of systems, let's say a binary mixture of
Gerhard, I'm sorry to interrupt you. I can barely hear you. I'm not sure whether it's just me.
Sorry. My microphone was up. Sorry about that, Thomas. You have a mixture of hard spheres, binary mixture of hard spheres, asymmetric, and then you look into the glass formation. So, not a driven system, but a system, so to speak, in equilibrium, and then you compare the results of both theories regarding this two-stage glass transition, right? And then you compare it also with computer simulation results. So I think all the three things exist. And then my question is, for this specific system, which of the two theories works better and why?
That's a good question. Louis did exactly that, I should say. And it's not evident which theory works better, I would say. There's a signature that, I mean, there's something that the theories predict differently and that could be probed. I mean, other than, okay, I mean, of course, you can now ask the shape of the transition diagram. I mean, which theory is a numerical better agreement or whatever. I have to say I'm not so much interested in that. The topology is something interesting, and that is a bit different between the two theories. And in the description of the partially arrested state, there is a difference that is qualitative and that could in principle be measured. And it concerns the fact that, so we are looking into a state where we call the species big and small, right? And the big particles, they arrest, so their self-motion becomes arrested. And the self-motion of the small particles doesn't. It still relaxes, they have a finite diffusion coefficient and so on. And what most coupling theory says is the glass transition, even into such a state, is a collective phenomenon. And in the collective modes, I pick up a non-ergodic signal in all the species. Because even the collective motion of the small particles will see that they are embedded in a non-equilibrium, in a frozen matrix. And the Langevin equation theory makes a different prediction there. It says, and the prediction becomes evident in what Magdaleno and others have called the propagator. So you don't look at the matrix of correlation functions as we are used to do. So we would say we make density correlation functions AA, AB, BB, and this is a 2x2 matrix. and these all become non-ergodic. But I can take this matrix and multiply with the inverse of the structure factor from the right. And if you, I mean, this is a quantity that appears in the form of a propagator in various ways of writing theory. And something funny happens in the self-consistent Langevin equation theory there. You get a zero eigenvector all of a sudden. And in mode coupling theory, you don't, because in mode coupling theory, you can show that both quantities are positive definite symmetric matrices. I multiply two of them together, they are still positive definite. So mode coupling theory says this propagator has also all non-ergodic components. And the Langevin equation theory says, no, connected to the small particles, there is a zero mode in the propagator. And this is in principle something that you could measure. What came out of the work that Louis and I did is that, yes, but even in mode coupling theory, the non-ergodic component that it predicts is extremely small. So mode coupling theory predicts something finite, but extremely small. And now I don't know what to think, because you could argue that predicting something finite but extremely small is an approximation error. Or you could argue that predicting zero for something that is actually finite but very small, like the Langevin equation theory does, is an approximation. So I honestly don't know.
But as a matter of principle, there should be no zero eigenvalue, right? Because it's an overdamped system.
And that's the thing. In the propagator, it's not evident. And there's one thing that I don't know how to resolve. I think the experiment to do is interdiffusion. If you have such a mixture of A and B, interdiffusion is a collective process. So mode coupling theory says it's collective, it arrests. So mode coupling theory predicts the interdiffusion to go to zero, even if you approach the mixed glass state, the partial glass. I would not bet anything on that prediction, because you can also, I mean, interdiffusion is the motion of all the B particles versus all the A particles collectively. And for that, in order to get rid of A-B concentration fluctuations, I could keep all the A particles fixed and just have the B particles move around. So I could argue there should be interdiffusion in a partially arrested glass state. And a long time ago with Jürgen Horbach, we looked at some simulations, and I think there is. So I think mode coupling is just wrong there. And it could be connected to that it predicts a tiny non-ergodic component where there actually shouldn't be one. So my idea was to say, okay, but then we know what to do. We take the self-consistent generalized Langevin equation theory and we calculate the interdiffusion coefficient. Unfortunately, as far as I tried, it doesn't work. And that's that would require a long discussion, I guess, on the structure of the theories and the structure of the vertices. So we don't know yet, but the experiment, it's clear.
Okay, good, thank you.
Okay, thanks. And just in the last minute, I will read just one commentary and one additional question, very brief, to Thomas. First, Jorge from Puebla says, sorry if the question is annoying. Perhaps I feel there is less connection that I may wish. It's the same person that was asking about the connection previously expressed. And he says also, well, sorry, I would love to take that approach. At the end, electrons taking as fermions are good enough for similar formula. And just the last question for you, Thomas, it's from Christian Valderas, which says, thanks to the organizing committee. And do you believe that we are close to find a finally theory to the glass transition problem?
So first to the comment, I mean, it's not an annoying question. And I know there are quantum glassiness phenomena that it's just something I've never worked on, but I think there is something interesting there that's worth exploring. And there are also very strong analogies to what we just discussed with Gerhard and medibody localization features. Are we closer to having a definite theory of the glass transition? I mean, I think we've all hoped that, and many in the audience have hoped that already 30 years ago, and then it turns out not. So I would be very cautious in saying that. At the moment, what I do think is that we have a pretty good understanding of what has been called the mode coupling crossover and why it's avoided and why the relaxation time does not diverge there, but just continues growing. But if you ask about questions that happen very deep in the glass, then I would have doubts whether either of these liquid state-based approaches is good enough to capture properties of the amorphous solid. So there is something going on at very deep temperatures, also concerning stress relaxation and the rheology of these systems that are not yet well captured in these approaches.
Okay, thank you very much, Thomas. And I will just ask the audience to give a virtual applause to your talk, because we need to move to the next talk. But thank you very much. It was very exciting to hear you.